Good morning, Year 12 Single Mathematicians. Just going to continue with Chapter 11. We're on 11.4, using integration. A couple of sub-chapters ago we were doing using differentiation, so we're just doing the second half of calculus, which is integration. And the main objective today is to use calculus to switch between acceleration, velocity, and displacement. So we are aware that if displacement, which I'm going to use the letter S to represent displacement, to go from displacement to velocity, which we're going to use V, we differentiate. So that would be equal to ds by dt. And then to go from velocity to acceleration, I'm going to use the letter A, we differentiate once more. So that would be dv by dt. And now, today, we have to go in the opposite direction. So if I want to go from acceleration to velocity, I have to do the opposite of differentiation, which is integration. I'm going to write in there, remember the plus c, that's something that people forget with integration, and we do need to use it. And then to go from velocity to displacement, we integrate again. Integrate better, plus c. There we go. So, yeah, that's pretty much it. You just go in the opposite direction. To go in the opposite direction, you integrate. Let's go straight into an example. We have a particle is moving on the x-axis, so on a straight line. At time t is equal to 0, the particle is at the point where x is equal to 5. The velocity of the particle at time t seconds is 6t minus t squared meters per second. So that's just a very long way of saying v is equal to 6t minus t squared. They've given you the formula for velocity. Find an expression for the displacement of the particle from the origin at time t seconds. So, to go from velocity to displacement, we integrate. So displacement is integrating velocity with respect to time, remembering the plus c. So integrate that formula, 6t subtract t squared with respect to time. And then integrate, add 1 to the power, divide by the new power. So 6t squared divided by 2 minus 1/3 t cubed. Remember the plus c. So this is a formula for displacement. It could be simplified, 3t squared minus 1/3 t cubed plus c. However, you need to work out the plus c. There's enough information given in the question for you to work out the plus c. I think you can spot it. When t is 0, x is 5. Or s. I've done. I might have to change that to x. It doesn't really matter if you use x or s, but looks like they're using x for this. So if you replace every single t value with 0 and replace every single x value with 5, we can work out the plus c. So when x is 5, t is 0, to give you 5 equals 3 0 squareds minus 1/3 0 cubes plus c, which gives you c is 5. So in other words, that formula, that expression for displacement would be 3t squared subtract a third t cubed plus 5. And that would give you the displacement at any time you like. Part B, find the distance of the particle from its starting point when t is equal to 6. Distance from starting point, in other words, displacement. They've just literally given you the definition of displacement there, but in words rather than saying find the displacement. And so we just substitute t is equal to 6 in. So when t is equal to 6, x is equal to 3 6 squareds subtract a third 6 cubes plus 5. Substitute that. So 3 6 squareds minus a third 6 cubed plus 5. 41 meters from the starting point. And that would be it. So the one thing that people do forget with these is the plus c. People forget about the plus c when doing pure mass integration. They forget about it a lot more doing mechanics integration. It's got to be in there, otherwise you're going to make some mistakes. Having said that, EG number 2 might be a little bit different. So we have a particle traveling in a straight line. After t seconds, we've got a velocity v meters per second given by this formula, 5 minus 3t squared. Time's got to be bigger than or equal to 0. Find the distance travelled by the particle in the 3rd second of its motion. Okay. Distance travelled by the particle in its 3rd second of motion. Now you might remember distance travelled from sort of the Suvat chapter that we did. So can you think of anything about working out distance travelled of a particle from that Suvat chapter? And hopefully what you'll recall is distance travelled is area under the graph, and that area under the graph continues even if we've got curves, so it would be area under the curve. So distance travelled will be the equivalent to area under the curve. But for which graph? That's for a velocity time graph. Area under the curve for a velocity time graph. So let's try and draw that. So to draw any curve, you should consider its shape. This is a quadratic. It's a negative quadratic. Second thing you should consider is the y-intercept, or the v-intercept, which would be when t is 0, and you'd get v is equal to 5. And the third and final thing is the x-intercept, or in this case the t-intercept, which would be when v is 0, or 5 minus 3t squared is equal to 0. If you solve this, add 3t squared, divide by 3, square root, plus or minus 5 over 3. There's enough information now to draw the sketch. T-axis, V-axis, it goes through 5, it goes through plus root 5 over 3 and minus root 5 over 3. That's a negative quadratic, so it's like this. Okay, obviously based on it being greater than or equal to 0, we only care about this section of the curve. Couldn't care less about this. Right, we want the distance travelled in the 3rd second of motion. What does that mean, the 3rd second of motion? So, 3rd second is another way of saying between t is 2 and t is 3. So between t is equal to 2 and t is equal to 3. Now what would that be on this sketch? Root 5 over 3 is 1.29. So 2 seconds is actually there, and 3 seconds would be a bit further. So it's actually, if I continue this sketch, it'd actually be that area there, which is below the x-axis. So to work out that area there, we have to use integration. So we would integrate the curve, which is 5 minus 3t squared with respect to t between 2 and 3. And that'll give us that area there, and that would be the distance travelled. So this is equal to 5 integrates to 5t, 3t squared goes to 3t cubed divided by 3. You could simplify that, just a t cubed, and that's between t is equal to 2 and t is equal to 3. And then you substitute the values in. Now for this one, if you notice, I haven't put the plus c in, and it's because for integrations with limits you don't need the plus c, because as you'll see, I end up doing a subtraction and the plus c's would disappear anyway. So 5 2's minus 2 cubes. If I had a plus c there, I'd have a plus c there and a plus c there, and they would subtract and disappear. So there's no need to put them in for what we call definite integration. Type that into calculate in one step. We've got 5 3's, subtract 3 cubed, subtract 5 2's, subtract 2 cubed, giving us a negative 14. Which does make sense, actually, a negative area, because areas below the x-axis are actually given us or worked out to be negative. But we want distance, and distance travelled in that 3rd second would just be 14. You make it positive, 14 meters, and that would be it. Okay, I'd like you to try exercise 11D, which is on page 190, and I'd like you to do the evens only. So just the evens only from page 190. We're getting very close to the end of this book, so it's really important now that if you've got any queries about anything, that you start letting me know, and then once we finish the course we can go back through and revise stuff before your internal exams. Right, remember to upload everything to Class Notebook, and I'll see you soon.